Here's something nobody tells you about Proxima Centauri. It's already dead. Not literally, but to human eyes, this star is invisible. 600 times dimmer than our sun, pumping out most of its energy as infrared heat you can't even see. Every astronomy article calls it hostile, radiation-soaked, impossible to colonize. They're looking at it all wrong. What if I told you this dead star is actually the most perfect power plant in the Alpha Centauri system? That those violent, atmosphere-stripping flares everyone fears are actually energy jackpots waiting to be harvested? That Proxima Centauri could power humanity's first true interstellar megacity, not despite its violence, but because of it? Welcome to the hidden energy revolution at the edge of our nearest star system. Chapter 1. The Invisible Star. Bond Suvo 34 points. Let's start with what Proxima Centauri actually is and why calling it dead isn't completely wrong. Proxima is a red dwarf, the smallest class of true star. It's only 12.5% the mass of our Sun, barely heavy enough to sustain fusion. In fact, if you took away just a bit more mass, it would be a brown dwarf, a failed star that never quite lit up. Its surface temperature is a mere 3,000 Kelvin compared to the Sun's 5,800. Now here's the really wild part. Proxima Centauri is closer to us than any other star in the galaxy, just 4.24 light-years away. Yet we can't see it with our naked eyes. Not even close. It has an apparent magnitude of about 11, which means you'd need a decent telescope just to spot it. The reason? It's putting out only 0.00056% as much visible light as our Sun. 0.0056%. But that's where everyone makes the mistake. They're measuring the wrong thing. When you account for all wavelengths, not just visible light, Proxima still only manages 0.2% of the Sun's total output. Over 85% of its energy comes out as infrared radiation. Heat, not light. To human eyes evolved under a yellow sun, Proxima might as well be dead. But to an advanced civilization? It's a slow-burning fusion reactor that will outlast the universe itself. Proxima Centauri will remain on the main sequence actively fusing hydrogen for 4 trillion years. That's about 300 times the current age of the entire universe. Our Sun? It'll die in about 5 billion years. Proxima is the tortoise to our Sun's hair, burning its fuel so slowly, so efficiently, that it represents the closest thing to an eternal star we could ask for. And because it's fully convective, meaning the plasma circulates throughout the entire stellar body, it mixes its fuel constantly, avoiding the helium buildup that kills bigger stars. It'll use nearly all of its hydrogen before it dies. Even better, near the end of its life, it'll actually get brighter for several billion years before transforming into a white dwarf. So yes, Proxima looks dead now. But it's the longest burning candle in the cosmic cathedral. Now let's talk about why everyone thinks Proxima is a terrible place to build anything. The flares. Red dwarfs like Proxima are violent. Their fully convective interiors generate powerful magnetic fields that twist and tangle in the star's atmosphere. When these fields get too stressed, they snap and reconnect, unleashing stellar flares. These aren't gentle solar hiccups. These are cataclysmic eruptions. In 2016, astronomers observed Proxima undergoing a super flare that made it 8.3 times brighter than normal. Just imagine standing on Earth when the sun suddenly becomes 8 times brighter. The infrared, visible light, X-rays, and ultraviolet radiation would be lethal. At Proxima B's distance only 0.05 AU, 8 times closer than Mercury is to our Sun. These flares are atmosphere-stripping weapons, and they're frequent. During observations of young red dwarfs similar to Proxima, astronomers detected what they called the Has flare, one of the most intense stellar flares ever recorded in ultraviolet light, more energetic than the most powerful solar flare we've ever seen from our sun. The terrifying part? They caught it in less than a day of observation, suggesting these superflares happen every day, maybe multiple times per day on young red dwarfs. Even though Proxima is older, about 4.85 billion years, roughly the same age as our sun, it's still active. About 88% of its surface shows active regions, compared to just a tiny fraction of the sun, even at solar maximum. Its corona temperature reaches 3.5 million Kelvin, compared to the sun's 2 million. A 2024 study of Barnard's star, another old red dwarf, found it was in a flare state 25% of the time. The conclusion every scientist reaches: planets around Proxima would have their atmospheres stripped away. Any life would be sterilized. It's a hostile, radiation-soaked hellscape. But here's what they're missing. What if you're not trying to survive the flares? What if you're trying to harvest them? Let me paint you a picture of a civilization that colonized Proxima Centauri, not for its planet, but for its star. The key insight is this: Proxima's weakness is also its strength. Yes, it only produces 0.117% of the sun's total energy output, but it's doing this in a package 1/7 the sun's diameter. And because it's so small, you can build your energy harvesting infrastructure much closer to it without cooking your equipment. Think about it. Earth orbits at 1 AU from the sun. Proxima's habitable zone, where water could theoretically be liquid, is at just 0.05 AU. You can build energy collectors 20 times closer to Proxima than we orbit our sun. And since radiant energy follows an inverse square law, getting closer is huge. If you can tolerate the heat, being 20 times closer means you're collecting 400 times more energy per square meter of collector surface. But wait, doesn't that mean you'd melt? Normally, yes, but here's the genius part. Proxima puts out most of its energy as infrared, which gives us options. A 2021 study in Scientific Reports examined the efficiency of various solar panel types under different stellar spectra. Standard silicon solar panels designed for our sun optimized for visible light with a wide band gap would be only about 1% efficient at Proxima Centauri. Basically useless. But organic photovoltaics with a narrow band gap, optimized for infrared collection, up to 12.6% efficiency. And this is with current Earth technology. An advanced civilization could do far better, even more promising. Thermoelectric conversion. Instead of trying to convert light to electricity directly, you let Proxima's infrared heat up a thermal collector to thousands of degrees, then use thermoelectric elements to convert that heat differential into power. At the temperatures you can reach close to Proxima, conversion efficiencies could hit 70–90%. One researcher studying red dwarf energy harvesting calculated that even if only 1% of the incoming energy ends up as usable power, you could place your generators at 1% of the distance between Earth and Sun, 0.01 AU, and still get the same energy output as 100 generators at Earth's orbit around our Sun. The economics are insane, but the real secret weapon? The flares. Here's where things get wild. What everyone sees as Proxima's greatest threat, an advanced civilization would see as a predictable energy windfall. Think about what a stellar flare actually is. It's a magnetic reconnection event that releases tremendous energy in a very short time. The Has flare that terrified astronomers? It released energy equivalent to 100 million nuclear bombs exploding simultaneously. Now imagine you have an orbital infrastructure specifically designed to capture that surge. Not to block it, you can't, really, but to absorb it. This is where Dyson swarm technology comes in, but not the kind you're thinking of. We're not building a solid sphere or even a complete shell around Proxima. We're building a distributed network of specialized energy collectors, each optimized for different parts of Proxima's output. The infrared harvesters. These form the base layer, floating closest to the star. They're essentially massive heat mirrors, lightweight statite sails that float on Proxima's light pressure, positioned to soak up infrared radiation and convert it via thermoelectric elements. They don't even need to orbit. They just float there, suspended by radiation pressure, slowly sipping energy. The flare catchers. These are the really clever ones. Positioned at optimal distances and orientations, these collectors are built to spike in energy production during flare events. They use superconducting magnetic field generators to direct the charged particles from coronal mass ejections into collection arrays. Essentially, they're turning Proxima's stellar wind into a particle beam power system. During a major flare, when Proxima increases its output by 8x, these flare catchers would see their power generation jump by orders of magnitude. It's like having a fusion reactor that occasionally goes into overdrive and gives you a free energy bonus. The UV absorbers. Positioned farther out, these specialize in capturing the ultraviolet and X-ray radiation that makes Proxima so dangerous. Instead of seeing this as deadly radiation, you see it as high-energy photons ripe for capture. Advanced metamaterials could convert these photons directly into electrical current with high efficiency. The beauty of this system is that it's scalable and modular. You start with a few hundred collectors. As you extract raw materials from Proxima b and the outer system bodies, you build more. Eventually, you have thousands, then hundreds of thousands of these collectors forming a partial Dyson swarm. The energy doesn't all stay at Proxima either. You beam it. Using a network of laser stations, you convert electrical power into tightly focused infrared laser beams and transmit them to Alpha Centauri A and B, just 0.2 light-years away, where the main colonies are. The transmission loss is minimal, a few %, and the beam provides constant, reliable power. So what do you actually build with all this power? This is where the vision of an interstellar megacity comes together. The first thing you need is materials, and Proxima b provides them in abundance. It's an iron-rich, rocky world with 1.3 times Earth's gravity. It's tidally locked, with one side forever facing the star and one side in eternal darkness. It has little to no atmosphere thanks to Proxima's stellar wind having stripped it away billions of years ago. Perfect for mining. You establish your first mining colonies in lava tubes on the day side, protected from the flares and micrometeorite bombardment. Mining crews, mostly robotic, but with human oversight, extract iron, nickel, and silicates. These materials get launched into orbit via mass drivers. With no atmosphere, you don't need rockets. A magnetic railgun does the job beautifully. On the dark side, you build something unexpected. A domed city, but not on the surface. You hollow out massive caverns, then construct pressurized domes deep within Proxima b's crust. Why underground? Radiation shielding. Several meters of rock is better than any man-made shielding, and it's free. Above these underground domes, you position orbital mirror arrays, hundreds of huge reflective surfaces in synchronized orbits. These mirrors have selective frequency coatings that filter out harmful radiation while reflecting Proxima's infrared onto ground-based thermoelectric panels. You can literally dial up or down the brightness and heat hitting your dome by rotating mirrors. During a flare, rotate them away. Need more power? Angle them for maximum reflection. The result is something surreal. A city on the night side of Proxima b that's actually brighter than the day side, lit by artificial sunlight that looks and feels like Earth normal, generated entirely by filtered and reflected starlight. But the real city isn't on Proxima b at all. The megacity proper is in orbit, a swarm of O'Neill cylinders and Stanford Tauri, massive rotating habitats providing artificial gravity through spin. These aren't small outposts. We're talking about cylinders 8 kilometers in diameter and 32 kilometers long, each housing hundreds of thousands of people in Earth-like conditions. These habitats orbit in a shell around Proxima, positioned at optimal distances from the energy collectors. They receive power via microwave transmission from the Dyson swarm elements. They receive raw materials launched up from Proxima b. They manufacture everything the growing colony needs: more habitats, more collectors, more infrastructure. The habitats themselves can rotate their orientation relative to Proxima, meaning they can simulate any day-night cycle they want. Want a 24-hour Earth day? Done. Want perpetual twilight? Also done. Each habitat can be customized to its inhabitants' preferences. Within a few decades, you're not looking at thousands of colonists, you're looking at tens of millions. Proxima's Dyson swarm is growing exponentially as more and more collectors come online. The megacity is consuming every asteroid, every comet, every loose rock in the Proxima system to build more living space. And the best part? All of this is powered by a dead star that will keep burning for trillions of years. Now here's where Proxima's position in the Alpha Centauri system becomes crucial. Proxima orbits the binary pair of Alpha Centauri A and B at about 13,000 AU, a fifth of a light year away. That's far enough that it's barely gravitationally bound to them, orbiting once every 550,000 years. For most purposes, it's almost a separate star system. But not quite, and that matters. You see, colonizing Alpha Centauri means colonizing all three stars. A and B have their own planets. Hypothetically, let's call them Aurora and Boreas, likely more hospitable for traditional planet-based colonies. These stars are brighter, warmer, more like our sun. That's where the main population centers will eventually be. But getting there from Earth requires enormous energy. The interstellar laser highway concept using powerful stellasers to push light sails to a significant fraction of light speed is the only practical way to move millions of colonists across 4+ light years. Here's the problem. Every system needs two laser networks, one at the origin star to accelerate ships, and one at the destination star to decelerate them. Building these networks requires tremendous infrastructure and power. But what if you could build just one network at the destination that services all three stars? This is Proxima's hidden advantage. Because it's gravitationally bound to A and B, even loosely, you can set up a laser deceleration network at Proxima that can also send and receive ships to A and B at local speeds. The 0.2 light-year journey from Proxima to the AB pair takes only a fraction of the time of the 4+ light-year journey from Earth. More importantly, Proxima's Dyson swarm can power the entire highway. You use the energy captured from Proxima's flares and infrared output to operate the deceleration laser network for incoming Earth ships, power the local acceleration lasers for traffic between Proxima and AB, beam power directly to the A and B colonies as they're being established. Essentially, Proxima becomes the energy nexus of the entire Alpha Centauri system. It's the power plant that makes everything else possible. And because of Proxima's extreme longevity, this network could operate for trillions of years long after Alpha Centauri A and B have died and gone supernova. Proxima will still be there, still burning, still powering the remnants of human civilization in this system. Let's zoom out and look at what we've really discovered here. For decades, everyone dismissed red dwarfs as terrible places for life or civilization. Too dim, too violent, too alien. The focus was always on sun-like stars yellow and orange dwarfs that looked and acted like home. But we were thinking like primitives, like creatures who needed their star to look pretty and feel warm. An advanced civilization doesn't think that way. An advanced civilization looks at Proxima Centauri and sees a fusion reactor with a fuel supply that will last 400 times longer than the current age of the universe. A relatively small star that allows close-in energy harvesting infrastructure, a power output dominated by infrared, which is perfect for thermoelectric conversion. Regular flare activity that provides predictable energy surges for specialized harvesting. A stable member of a triple star system, providing redundancy and local travel options. Abundant rocky materials nearby for construction. Most importantly, they see a star that won't die. Not for trillions of years. This isn't just a colony, it's the foundation for an eternal civilization. Think about what that means. Humanity could build its first city at Proxima Centauri, and that city could still be there, still powered by the same star when our galaxy collides with Andromeda in 4 billion years. It could still be there when the last natural stars in the universe begin to flicker out in the far future. This is the secret that red dwarfs hold. They're not failed suns. They're not inferior. They're the ultimate survivors of the cosmic lottery, and they offer something no other star type can. Permanence on a scale that defies human imagination. The dead star at the edge of Alpha Centauri isn't dead at all. It's humanity's best chance at immortality. So the next time someone tells you we should colonize Alpha Centauri, remember this. We won't be going there for the bright, sun-like stars at the center. We'll be going for the invisible red dwarf in the outer darkness. Proxima Centauri dim, violent and deemed impossible, will become the engine of our first interstellar megacity. Its flares will power our energy grid. Its infrared glow will warm our habitats. Its unimaginable longevity will guarantee our descendants a home long after Earth's sun has died. The future of humanity doesn't orbit a star that looks like ours. It orbits a star we can't even see with our naked eyes, a star everyone said was dead. They were wrong. Proxima Centauri isn't dying. It's just getting started, and so are we.